Hey everybody, welcome to Foundations of Science. This lecture is on basic Earth structure, and I'm going to focus on the sort of thing you need to know, not so much about just Earth structure that you may have learned in high school, but more about what the Earth structure has to do with earthquakes, so we can better understand what we need to do to predict earthquakes and eventually save lives. As you probably have heard in different lectures, the solar system was formed by a supernova, and as these gases coalesced, they eventually formed into the planets we know in our solar system. If you want to know more information about this, talk to Professor Penpraise. As this debris that floated around the early solar system coalesced, it started to form planets. Sometimes violent collisions resulted. This is a picture image, artist's image of the early Earth being hit by a moon-sized object, spewing out a bunch of hot molten material that eventually formed our moon. The Earth's structure can be classified two different ways. First is by chemical composition, the second is by physical properties. In this class, of course, we're going to be more concerned about physical properties, but the two really can't be divorced from each other. We'll talk about that a little bit later. If you look at chemical composition, eventually the lighter stuff floats to the top. So the continental crust tends to be made of granite, where oceanic crust, which is a little bit denser, tends to be made of basalt. Once you get down to the mantle, we have mostly iron and magnesium silicate minerals, and by the time we get to the core, it tends to be metal, which is solid. Well, the inner core is solid, the outer core is liquid. It's made up mainly of nickel, iron, and sulfur. So again, the Earth's system classified by chemical composition includes the terms crust, mantle, and core. Crust is usually granitic and basaltic. Mantle is made up of iron and magnesium silicates. The core is made up of most molten metals, mostly iron and nickel. The outer core is liquid, and the inner core is solid. When we look at the Earth's classification by physical properties, we use slightly different terms to refer to what we call the rheology of the material. The lithosphere is the top part that we sit on. Litho is from rock, so it tends to be hard. The asthenosphere is what sits below it. It tends to have what we call a plastic rheology, and it forms like a plastic would. The mesosphere tends to be rigid. It's in between. It's not really plastic, it's not really solid, but it's in between. Some people argue the mesosphere doesn't really exist, and they consider the asthenosphere between the lithosphere and the core. The core has the same names as the chemical composition. However, the outer core is liquid. We can talk more about how we know that in a minute. And the inner core is solid. The way I like to think about rheology is, what kind of noise does it make when you hit it with a hammer? When you hit a rock with a hammer, it makes a crack. When you hit the asthenosphere with a hammer, it makes a thud, just like you're hitting a piece of plastic. When you hit the outer core with a hammer, it would make a splash, has about the viscosity of water. And when you hit the solid metal, iron and nickel inner core, hit it with a hammer, it makes a ring like a bell. So reviewing quickly, hit the lithosphere with a hammer, it cracks, it's a rock. The asthenosphere, hit it with the hammer, it actually makes a thud. The outer core makes a splash, the inner core makes a ring. The beautiful thing about looking at earthquakes in geophysics is you need to memorize exactly two rock types. The first one is what we mostly stand on the continents, which is above ground, and it's called granite. The second is a little bit more dense, made up of more dense mineral constituents, and it's called basalt. As far as geophysicists are concerned, there are two types of rocks, granite and basalt. That's all you need to know. So how do we know about the Earth's rheology is a really interesting question, but we need some source of energy that's strong enough to get through the entire Earth, and earthquakes can do that. Send an earthquake through, depending on the rheology of the material, how it deforms when it's hit with a source of energy, we can determine the actual material properties of the Earth. The outer core, the lithosphere and the asthenosphere are both technically solid, which means they can propagate both what they call P waves and S waves. P waves you can remember as either being primary or pressure waves. These are like sound waves is a good example of a pressure wave, where the molecules of rock, or in the case of sound, air, bang back and forth. They expand and contract in a way that propagates the energy. Shear waves, S waves or shear waves or secondary waves, are ones that go side to side. You can think of them kind of like ocean waves, but that's a little bit different. Those are actually surface waves we'll talk about in a minute, but they're the ones that go side to side. So if you push a table, it moves in a side to side direction and propagates displacements in that way. The main difference between P waves and S waves, other than the fact that P waves are faster propagating, they have a faster velocity through the same material, is that shear waves cannot go through liquids. Imagine if you took your hand and waved it in front of your face. You know that shear waves cannot propagate through a fluid, liquid fluid, which air is, because your face doesn't move when you move your hand in front of it. If you, however, carefully move your hand very rapidly in front of your face toward your face, you can't actually feel the wind or a breeze on your face. That tells you that pressure waves, the pressure of the wind, can actually get through there. What defines a fluid is the fact that shear waves cannot propagate through it. If we have an earthquake that occurs in a certain location on the planet, there's what they call a shadow zone, where only P waves make it through the Earth, and shear waves cannot make it through because they refract off of the outer core and bend around to other sides of the Earth. Had they been able to go straight through both P waves and S waves through the planet, we'd know that it was solid all the way through. I mentioned before that the Earth is made up of exactly two types of rocks. Heavier rocks or more dense rocks, the basalts, sit lower in the water, and that's why there are actually oceans around. The less dense rocks, the silicates that make up granite, float higher on this plastic asthenosphere. So this is important because when we start talking about earthquakes, the biggest earthquakes in the world occur in subduction zones, and this is where more dense oceanic crust sinks beneath less dense continental crust. The plates on the Earth move around. Okay, going back to our Earth structure. The lithosphere of the Earth is broken up into many, many different lithospheric plates. These plates are shown in this slide where they're connected by different boundaries. Now, it's curious that the Earth plates are actually broken up into these different bits, but they actually move around on the surface, and they could move around kind of independently unless they were broken into plates. Why they move around is a really interesting question, which we'll explore in a little bit later. But the fact that they do move around, and they're moving around on a curved surface, are what defines what kind of earthquakes you're going to get in different places and how big those earthquakes are going to be. So you can see in this image in front of you, the North American plate is one of the larger plates that exist. The Eurasian plate is another very large plate. Pacific plate in the middle of the Pacific Ocean is an oceanic plate. Nazca plate, Antarctic plate, South American plate, African plate, and the Australian plate are all the major lithospheric plates that are on the surface of the Earth. I don't really care that you memorize these. I just want you to know that these different plates exist, and where they come together are where the earthquakes are. I'm going to repeat that. Where the plates come together and slide past each other or underneath each other, or they split apart from each other, are where earthquakes occur. This image is a little bit busy, but it shows a lot of the different kinds of plate boundaries. The orange arrows in the middle of the screen show a divergent plate boundary. These are where the mid-ocean ridges spread apart and actually create new oceanic crust. Because you're creating new oceanic crust and the Earth is not actually getting any bigger, you have to recycle that oceanic crust somewhere else. Now, we mentioned before, oceanic crust is made up of basalt. Basalt is more dense than continental crust, made up of granite, So when the two bang together, the oceanic crust tends to subduct or get pushed beneath the continental crust. This is what we call a subduction zone, and again, this is where the biggest earthquakes in the world occur. There's kind of an odd type of plate boundary called a transform plate boundary. This is a real function of geometry. This is something perhaps we should talk to Professor Barrick about. But when you move plates across a curved surface, sometimes you just need to accommodate that movement, and the plates tear apart. They form these sliding faults where they move past each other alongside. These transform plate boundaries tend to occur within oceanic or continental plates where there's no density contrast between the two different plates. Because of this, they tend to be sort of medium-sized earthquakes where the divergent plate boundaries tend to produce somewhat smaller earthquakes, but the largest earthquakes occur at the convergent plate boundaries. This image also shows what drives a lot of this plate movement on the surface. Remember we saw the supernova that was formed the early solar system. Well, as the planet started to coalesce and cool, it formed an insulating rind over the Earth. This insulating rind is, you guessed it, the lithosphere. Beneath it, this plastic asthenosphere tends to be a lot hotter, and because it's hotter and the core is even hotter than that, there's actually convection cells that are set up in this plastic material. Now, over geologic time, we're talking about extremely slow rates of movement here. Movements of the plates over thousands of kilometers tends to be about as fast as your fingernail grows. But what's driving it in this case are these convection cells where heat from the outer core tries to escape, hits this insulating rind, that gets pushed back down, cools off a little bit, and forms these beautiful cells. The traction that exists between the asthenosphere and the lithosphere is what pushes the plates apart and together the different plate boundaries. The other part that drives plate motion is subduction zones. We mentioned that these really stop. You gotta be kidding me. Why would they do that? So this is actually a better picture of a plate tectonic subduction zone ridge complex. You can see the convection cells merge at the oceanic spreading ridge, diverge there, pushing the oceanic lithosphere down beneath the continental lithosphere. You can see where the two come together often is a trench, and that's where the big subduction zone earthquakes occur, between 8 and 9 on this diagram. Other features of subduction zones include volcanoes. We'll talk about that maybe in another class. We're not going to talk about much about volcanic eruptions much during this class. I like this image better than the previous one because the subduction zone is actually pointing in the right direction, where on the other one it was backwards. So bringing it all together, this is an image of the entire Earth. You can see a solid inner core made of iron and nickel, and it tends to be very hard and rings like a bell if you hit it with a hammer. The outer core is a liquid nickel iron alloy, has convection cells in it, and if you hit it with a hammer it makes a splash. The lower mantle, in this case, is made up of iron and magnesium silicates, but we're going to refer to that as the asthenosphere, which is a plastic rheology. You hit it with a hammer, it makes a thud, and on top, floating on top of the whole thing, is the lithosphere, where most of the earthquakes occur. You hit it with a hammer and it makes a crack. That's all for this lecture. The next lecture is going to go into how plate tectonics comes together and make earthquakes.